Thank you so much. Hello, everyone, and I'm here to talk about software design. As a part of this talk, I'm going to share some concepts that you can use to think clearly about software design and come up with better design. While this talk is suited for someone who's actually started doing design, if you're just starting to learn and starting to do software design, you can also benefit from this talk. So what I'm going to do is, before I dive into the talk, just so that we get everybody on the same page, I'm going to cover 5 themes about software design, so that all of us are on the same page. And I'll use these 5 themes as overarching themes throughout this talk. So with that, let's get started, right, with the 5 themes. The first theme I want to highlight is problem solving. One of the key aspects of problem solving is you have a large problem. You break it into smaller pieces to solve it, right? So you take a big problem and break it into smaller pieces to solve it. You do this for 2 reasons. One is to reduce complexity, because a big problem is harder to solve. So once you have smaller problems, it's easier to solve. The second reason you do this is that once you have these smaller chunks, you can actually distribute them to different people to solve. So that's one of the key aspects of problem solving, which is problem decomposition. You do decomposition to solve a problem. When it comes to software design, the way we generally do it is you start with defining a high-level architecture, then go into defining the design of various components in their architecture. And then you take each of those components in the high-level design and go develop the low-level design. And then from the low-level design, you start writing code. So that's how you decompose something like a pyramid. You start with a big picture, and then you kind of go deep in. And once you write the code, the compiler takes the code and converts it into assembly code for execution. So the 5 themes, right? The first one is problem decomposition, which is you take a large problem, break it into smaller pieces. That's the first theme and first element of software design. The second aspect is this: software design is all the way from architecture to code. So the code is also design. Because code is not the final software. The final software construction happens by taking code and converting into assembly. Right? So design is not the working instance. Architecture to code are not the working instance. The assembly code is the working instance. So design is all the way from architecture to code. Usually, architecture, high-level design, and low-level design are not code. They are documents. But at times, they can be code too. And for small projects, you generally may not do all of them. For example, let's say you're implementing a binary search tree. You really don't need to do architecture design. But as for larger projects, and when you want to work with multiple engineers, you have to actually do this. So the second theme that I want all of us to get on the same page is architecture to code is design. The third aspect that I want to bring out is the design aspect, which is architecture to code. It's for humans. It is for humans. The humans are the primary audience and not machine. Compiler takes the code and creates assembly code, and that's for machines. Right? So this is the third aspect. So design all the way till code from architecture is for humans. The fourth aspect is design guides software evolution. So as you move towards the left from assembly code to architecture, you're doing that more for the future than today. You're doing that because you want software to be maintainable. So let me take an example. I can directly write things in assembly code, but it's just not maintainable. Even after some time, even I won't be able to understand what I've written. So as you move up, a code is a little more readable. So as you move up, you're doing it because you want to work as a team, and you're doing it for the future. It's for software evolution. So the fourth one is design guides software evolution. The fifth one is the initial cost, right? The software cost follows a pattern like this, right? So initially it starts with 0 and then goes up, and over the period of time, it follows a curve like this. And the key idea here is the initial cost is usually much lower than the cost for maintenance, evolution, and enhancements. And generally what we try to do is try to keep this curve constant, or try to reduce the cost too, right? But generally this is what happens if you... Now, with that, the 5 themes I want to talk about are the 5 themes which I want all of us to be cognizant of as we go through the talk are these, right? Software design is problem decomposition. architecture to code is software design. Design is for humans. Design guides evolution. Design is for the future. And software cost increases with time. Initial cost is usually way lower than the cost of evolution. So keep these 5 themes in mind. With these 5 themes, I'm going to, this was to get all of us on the same page. And now going back to the actual content of my talk is I'm going to cover 7 concepts that you can use to think clearly about software design. These are concepts that I've learned through experience, which will help you reason about software design better. While this talk is usually generally focused on the architecture and the high-level design and low-level design side of the spectrum that I showed you earlier, the concepts equally apply to low-level design, including code. But take all of them with a pinch of salt, right? Evaluate which ones make sense, which ones don't, and use them. And I've come up with these 7 because I think these are where engineers make a lot of mistakes. They can be more, but these 7 are ones where I believe a lot of mistakes happen from my experience. So that's how I've come up, but keep that in mind. So with that, I want to talk about another, my favorite thing. I will keep using 7 plus or minus 2 throughout this talk. And that, that my fascination for this came up from this paper in psychology, which is the number of, it's one of the, it's one of the highly cited papers in psychology. And it says that the number of objects an average human can hold in short-term memory is about 7 plus or minus 2. And remember, one of the themes I spoke about is software is for humans. So I'm going to use 7 plus or minus 2 sprinkled throughout my talk. When I talk about understandability, readability, reasoning, and so on. So I'll keep touching upon this, and this is something for you to kind of read. So with that, let's jump into the talk. A lot of context, so let's jump into the talk. The 7 aspects that I want to cover are these: mental model, abstractions, design tenets, one-way, two-way door, design span, flexibility, and elements of reuse. So let's go over each one of them one by one. And the way I do it is in each one of them, I try to give a real-world analogy, and then I'll talk about a software example and leave you with some takeaway points. So first is mental model. Mental model is an explanation of how something works, right? Mental model gives you the ability to visualize. So again, let me explain mental model with a real-world analogy before giving you a software example. And all of us know this is a very popular analogy. All of us know the periodic table. Periodic table is an arrangement of elements according to their recurring properties. Dmitry Mendeleev published the first recognizable table in 1869. The elements were arranged in a particular, according to the atomic number, with 7 periods on the side. And this is an example of a mental model. And here is why. Because there were many arrangements possible. You could have taken, these elements and arranged it in many ways. But this pattern added a lot of value and brought a lot of insight. So let's see how. Now, it gave, in my view, it gave like 2 main benefits. It gave you something that made it easy to reason about, and there were gaps which led to discovery of new elements. So let's see how both of these came about with this periodic table mental model. When Mendeleev proposed the periodic table, he noted there were gaps. Not all elements were discovered then. Now, the gaps provided a reasoning for scientists to discover the missing elements. Now, one can argue with that without gaps, we would have still discovered these elements. But the gaps made the job easier. The gaps gave you constraints to look out for. Like, for example, the number of protons, the missing element, what type of missing element, and so on and so forth, right? So the mental model, the periodic table mental model was essential for discovery of new elements and an ordering of that form. It gave you simplicity, and this model holds good even through today, and actually has led to all the way evolution, all the way to till quantum mechanics. So with that, let me with this as a real world example, let me dive into a software example. Like, how do you use a mental model in software? Now, one of the key thing is when you design, don't couple the design to the problem domain. Don't directly couple the design to the problem. Instead, take a step back and put a mental model in between. Then map the design to the mental model, and then map the domain to the mental model. Now, what is a mental model in this context? It's the way I would say, their mental model are the concepts behind the requirements. They're the why behind the requirements. And they sort of give you a decoupling from the domain and the design, allowing each one of them to evolve independently. Right, so it's very similar to the periodic table example, where the requirement was to arrange the elements, but arranging in that fashion gave a lot of value, and the fact that it still holds good today is a solid mental model that did not change. So with that understand, this is tricky. Getting the mental model is tricky. Sometimes the difference between the domain and the mental model is not very obvious. But let me explain with an example that'll give you more insights on what it is. With a software example, let's say you have a KYC as a problem domain, and your e-commerce website, and you have customers and vendors who come and use your platform, and you want to do KYC of the customer. Now, your product management comes and tells you, hey, do KYC of our customers. And as a part of that, they give you 3 requirements, which is collect selfie, collect an identity document, and verify if the age is greater than a certain number. Now, and these are the 3 requirements. I'm just simplifying the use case to explain the mental model. One way you would design this is directly map it to the design components. So in this case, I can take the selfie, map it to a selfie component. I can take an ID doc, create an ID doc component, an age check component. So there's no mental model here. You are directly mapping it, and this is fine for most cases. But what happens is, as the number of components increase, as the number of requirements increase, the number of components will increase, and this will lead to duplication and incorrect evolution, which I will show you subsequently. But let's understand how we can apply a mental model to this. So what in this case, when you have ID doc, selfie, and age, the first thing you want to do is, when you get a requirement like this, the first thing you want to do is ask, why are we collecting a selfie? Why are we collecting an ID document? And sometimes the answer may not come with one why. So in this case, if you go and ask a PM, why are you collecting ID doc and a selfie? The PM would answer saying, yeah, this is a compliance requirement. But then you need to take a step back and again drill down and ask, why is it a compliance requirement? And then start peeling the onion to get to the actual concept or the why behind the requirement. In this case of KYC, a good mental model is this: like, you identified that you had a customer who was an online customer on your e-commerce platform, and you had a real world user. So the reason you're collecting selfie and ID doc is to map the online customer to a real world customer, or map the online identity to a real world identity, right? So that comes in as a mental model, and we'll see why this is useful. But that is a possible mental model. Similarly, age has nothing to do with doing this connection from online to physical. So age is, let's just put it as a product rule for now. With that, great, we just added these two. What benefit do we get? Now, you can now take the mental model and create a design. And in this case, you come with 2 components. You call identity establishment, which is connecting a online user to a physical user. That's an identity establishment. And you have a product eligibility, which is doing some product checks. So you've come up with 2 components. So as opposed to earlier, where you kept adding components, here you have only 2, right? But is that the only benefit? Well, let's see, right? In my view, there are 2 main benefits you get out of putting a mental model and connecting that to the component. The first is this, right? It reduces the change blast radius. So what you've done is you've decoupled the requirements of the design, and you're not tightly coupled to the requirement. So let me explain that with an example. Let's say you had 3 KYC requirements: KYC 1, KYC 2, and KYC 3. In KYC 1, you're just collecting ID and an age, ID document and age. In KYC 2, you take an ID document, a selfie, and age. And in KYC 3, you take an ID, you take a fingerprint, and you take an age. So these are 3 separate KYC requirements. And they look like different requirements. And in the earlier case, if you did not have a mental model, you'll start adding components for this, right? But now let's see with our identity establishment as a mental model, how this helps. You can now, now you know that identity establishment is about connecting the online user to the real world user. So if you're just collecting ID in case of KYC 1, it becomes a weak identity establishment. It's not very strong because it's just collecting ID. It's possible that the user could have given some other, someone else's ID. So it's not very strong. On the other hand, if you're taking ID and fingerprint from the user, it becomes a strong identity establishment. And then ID and a selfie, just capturing a photo, could be a medium identity establishment. So what this has allowed you to do is it's allowed you to evolve, decouple your design from the requirements. So you can map multiple requirements to the same mental model and then map the design to the mental model. You achieve that decoupling. That's one. The second thing this has allowed you to do is it helps in software evolution. Again, going back to the themes, I talked about software evolution as the number 4 theme. And in this, the way it helps is, let's say, you want to define a new type of identity established. We know weak, medium, and strong, we saw that. Weak was just ID, medium was ID plus selfie, strong was ID plus fingerprint. But now you can go and define another strong identity establishment, which is ID plus selfie with liveness. So you capture a selfie and you actually verify if there's with liveness detection whether the real user is actually giving that selfie. So what this allows you to do is you can plug that in as another way to do strong ID establishment. So your software now evolves. You have an evolution path. You don't have to build this out, but you have an evolution path. Now, the other way the evolution comes as new requirements come in. Like let's say you get a is US citizen check. Again, you start applying these whys to understand the mental model, and even at the first glance, it's fairly obvious that connecting the online identity to it's probably not for identity establishment, right? Is a US citizen maybe a product rule, so you kind of want to put it there, but you have to still ask more questions and understand the context. Similarly, sanctions check. It's probably not identity established is not a product rule. It's probably something new, probably a compliance check, right? Again, you want to ask those questions to see how that goes. So with that, let me go to the takeaways of mental model. The first takeaway is identify the mental model from the domain, design to the mental model. This allows you to build thought leadership and verify, are we building the right thing? And what this gives you is it reduces the blast change radius of change. It guides software evolution. So when you have a design document, look for a mental model, have an explicit section there talking about mental model as you review or make your design. So with that, let me go to the next one, which is abstractions. And I'll talk about an abstraction with an example. Let's say you have a website where customers perform actions. In the same KYC use case, you want to record all the actions that were performed with the customers, so all the clicks and so on and so forth. So you're asked. That's a requirement. You're asked to build an audit component. So an audit component looks somewhat like this, right? There's an audit component that records all actions by customer. But I'm asking you to design the audit component. So how will you go about designing the audit component? One way is go back to the themes. Software design is problem decomposition. So now you have a big box, you're going to actually decompose that. So one typical way I would see people decompose this is into 3 components. And here I'm using AWS technology. So I've decomposed the problem into an API gateway, data store, and SNS. So API gateway handles the requests from the front-end website, and it takes the request and sends it to DynamoDB, which is a low latency, high throughput data store. And then SNS is for publishing. It's a message broker to publish messages. So those are the 3 components you have come up with. This is a fair way to decompose. So what I've done is I've taken one big problem that I had, which was collecting some audit records, and I've created 3 components. Is this the only way to decompose? That's the question. Now, if I look, there's another way to decompose. I can still have 3 components, and I can, instead of the API gateway, which was the AWS technology, I can say I just need REST APIs. And then I need a low latency store. It can be anything. And then I need a message publishing system. So what I've done, this is another way to decompose. I've used different names, same number of components, but this is another perfectly valid way, and this works. Now, third way is something like this, right? Which is I talk about, great, I have a audit component. So what I need is a system that will handle all the audit requests. So that's a audit request handler. Then I have a data store, which becomes the audit store. Then I have an audit notifications, send notification. So this is also another fair way to decompose. So what you've seen multiple ways to decompose a problem, right? And that's where abstractions come in. You've seen multiple ways. In this case, I showed you 3 examples of how it will work. And in all the 3 examples, I had 3 components. But why not 7? Why not 7 plus or minus 2? Why not like 20 components? Why are 3 components right? And which approach? I showed you 3 approach. Which approach is correct? Now, and that's where abstractions come in, right? Why abstractions are important? Abstractions guide you in these decomposition. It guides you in reducing complexity. Before I explain abstraction, one of the things I want to call out is that clearly in all the three approaches that you saw, naming was one very key aspect. Like you use different names, right? So name is definitely a key aspect of abstraction. So let me explain naming with a real world analogy. So in this case, so let me give you a real world analogy. Let's say there are a bunch of chairs, and that's how I draw my chairs. There are 20 chairs, and there's a stage. And I ask you to name this, right? So let's start with understanding a real world and see what happens. I ask you to name it. There are lots of names possible, but looking at this looks like a classroom. So you would possibly call it a classroom. But now I tell you, you have only now 15 chairs, but at one side there's a very, very long kitchen. And I ask you to name it. There are multiple things. It's very clear you can't call it a classroom now because there's a kitchen, there's a stage, there are chairs. It looks like something weird. So the first thing you would tell me is this is not possible. There's nothing physically that can exist like this. So you're just making things up. It's not a real world. It's not an abstraction of a real world. That's the first thing you will tell me. But let me actually show you, if I actually take you to a place and show you a room like this, which has chairs and a kitchen, and now I tell you, name it. Now there are three possibilities. And all these three possibilities are on three ends of a spectrum. So what would happen is the first possibility is you go to one extreme end and call it a room. It's a very, very generic name, right? Just fits in. Like tomorrow, if I go and add a living room there, then the name would still fit in. Or you go all the way to the other end and you call it, you start concatenating, like you call it classroom plus kitchen, right? So there are two extremes possible. You give it a generic name, or you go all the way to the other end and give it keep concatenating names. But the thing is, this real world example is how this is what we face every day when we do class design and software design is how do you name something, right? Which end do you go to? Now, but in this case, coming back to this case, those are two extreme spectrum. But maybe something you're missing. There's a concept you're missing, and that probably this is a culinary classroom where a chef comes and teaches other budding chefs and they do a hands-on exercise to practice cooking. Maybe it's a new concept, right? You haven't thought of, and maybe that is probably a right name here. Now, what you have done here is just a simple example like this. What you've done is you thought hard about a new concept and established, in my view, the right level of abstraction. You had a spectrum, but you established the right level of abstraction. But the important point is why is classroom, room, or concatenating classroom plus kitchen not a good choice? Why are they not good abstractions? And why is this important? Using the wrong name reduces readability, right? Obscures the intent and results in software bloat. Let's say you used a room. It opens up avenues to add things that don't relate to it, right? In this case, I can go add a bedroom. And making it too specific causes problems at the other end of the spectrum, right? Each time you want to add something, you end up creating a new object or a new class. So, a common pattern that I see, especially in software, is, when it's hard to name something, they just name it a manager, a component. Now that's a problem, right? It clearly does not indicate the responsibility, and over a period of time results in software. Go back to the themes I started with. Evolution. Software design is for evolution, and putting the right name is for that evolution. So take a step back, challenge yourself, see if you're going on either ends of the spectrum, and try to come up with the right name. But coming up with the right name is also depends on the domain and what problem you're solving. So let me give you this analogy. It's a very good read, which is a map is not the territory. I've shared the Wikipedia link here. And the thing is, the map is an abstraction of a reality. So think about this, right? Your map is always a reduced version of the reality. And imagine if you had a map that was 1:1. That map would never be helpful because you need a map because you want a reduced view. Now, which means map is not perfect, right? Map is a reduction. So what you see in reality is you cannot put everything on a map. And that's one point. And the second thing, there are many maps possible. For example, if you have a map of a country, it depends on, if it's a general map, you would highlight important cities. Now, let's say if it's an airline map, you would not put cities, you'll probably put the airports there. And let's say if it's a map to show telecom network, you'll do something else. So even the abstraction, right? Abstraction is a reduction, and even the abstraction depends on the context. The domain plays a very key role on which abstraction is correct. With that, if you go back here, because I knew customer audit as a problem, the three examples I gave, assuming with that simple requirements and with my domain, I would say something in the middle is probably the right abstraction. And if you go on the on the left, it's probably over, and on the right is probably under, right? So there is a spectrum of over and under. Keep this in your mind as you craft abstractions. With that, some takeaways on abstractions. First is look for over and under abstraction. Verify if there's a domain correlation. Look at the map example. You need to have a correlation. Verify if the abstractions are technology choice agnostic. I mean, then you have a problem there. And verify if the abstractions are too specific or too generic. Use these as tests. This is a tricky piece because you want to use all of these as tests to see which one works and which one doesn't. Sometimes you have to apply more than one to arrive at the right abstraction. But use these as litmus tests to verify if the abstractions are right. Right. So with that, I've covered two things that you want to look for. One is your mental model, and the second one is abstractions, right, on your design. And sometimes abstraction doesn't, it's not a separate section, but it is often, it's throughout your design document. The third thing you want to look for, and this is a documentation aspect on your design, are the tenets, design tenet. What are tenets? A tenet is a principle or a belief. Tenets codify the criteria, assumptions that were used to base your design. Design decisions make sense in the context of tenets. They're like constraints for your design. Go back to the constraints on the periodic table example. They're constraints, right? And design, more importantly, get everyone in agreement about critical questions that cannot be verified factually or require judgment. And tenets also indicate how you want to evolve software. So with that, what I would want to do is I'm going to give you 4 tips on how to write good tenets. What should you look out for? First thing you want to look at, take 7 plus or minus 2, as the number of tenets you have. So stick to an upper bound of, plus or minus 2, right? Because if you stick to an upper bound, it forces you to decide which tenets are important or which tenets aren't. You don't want to list all the tenets, but understand which one are important, which one are not, because the tenets are going to be used by the team, by your engineers in a day-to-day basis. Readability becomes important, and keeping things in working memory is even more important. The second thing is order the tenets. So you always want the tenets to be ordered. The reason is that the reason you order is because you want to create a tension between tenets. You want to know which tenets are more important than another. Ensure each tenet stands on its own, right? And the last, ensure that each tenet takes a stand, which means it doesn't state the obvious. It takes a stand declaring you care about one thing more than the other. So with that, what I'm going to do is I'm going to give you some examples of tenets to leave you with, and towards the end of the talk, share more. But in this specific case of KYC as a problem, going back to the KYC as a problem, if I'm building a KYC system, one of my top tenets would be security, right? And the way I would write something like this is security of my system is my top priority. We'll sacrifice availability if required, but never compromise security. So look at this, right? And the 4 things that I talked about, it gives you a trade-off between the tenet, right? The tenet gives you inherent tension within itself. It takes a stand, and it gives you an idea. Now you can use this to design your system, and you can use this even while you're operating your system, right? And let's say there is a security incident that has happened. What would you do? You would use this tenet and say, okay, I'm going to this is my high priority. I'm not going to keep the security. If the security incident is going on for a while, you'll say, okay, no, let me shut the system down, because that's my tenet, right? So this helps you in software evolution, maintenance, or operations, connecting back to the theme. So that's on tenets, right? And so with that, we've covered 3 things, and I'm now going to go on the 4th thing, which is one-way, two-way doors. And as a part of one-way, two-way doors, I'm talking about reversible and irreversible decisions. That's what I'm saying. What is the reversible versus irreversible? So you want to start looking for one-way, two-way doors throughout your design document. and see which ones are there, right? And the key, the key pitfall or thing to watch out for is a one-way or two-way door decision, makes sense in the context of a time frame, right? For example, even plastic is degradable, if you take few hundred years into account. So every one-way door can be a two-way door if you give it sufficient time. So keep that caveat in mind. But just to give you a feel of what one-way, two-way doors decisions you have to look out for, let me give you an example of three. And let's see which ones are one way or two way. Incorrect abstractions. We just spoke about abstractions as a number two. Incorrect abstractions is this a one way or a two way door? In my view, it's a one way door, but it's very, very hard to go and fix it. Yeah, if you have sufficient time, you can go deprecate and write the new software. But if you get it wrong at the beginning, it's super hard to go back and fix it. So that's clearly a one way door. So you want to focus a lot on abstractions in your design. Not writing unit tests along with code. This one is a debatable one. I know a lot of people, and I would say this is a gray area between a one-way and two-way, but I would actually put it as one-way because you can write good tests along when you write the code. Ideally, you should write the test first and the code, later. You should follow TDD. But if you write, if you go and write code without tests and try to write tests later, that doesn't work because it's very hard to write good tests, and sometimes you won't go back to doing it. So I would actually put it as a one way. And third one is going with a static storage of configuration instead of dynamic. I would call this a two-way door, and here's why. If I have good abstractions and I have isolated the the configuration component, but if I just store it as even a local file and then move it to a store to update, to allow management of configuration, that kind of makes a lot of that simplifies a lot of things when you have to deal with that. So that's a two-way door. You can take it out. It's an isolated piece with well-defined abstraction. You take it out and replace it. So these are some example of decisions that you look for, and what you are supposed to you want to look for these one-way, two-way doors throughout the document. So usually I keep this one, all the 7 things I keep it in mind, and like the phases of compilers, I run them each time. So I look at mental model first time, abstraction, and then finally, one-way, two-way doors. So that's one usual thing I do, but keep that in your mind. So with that, I would say the key takeaway from this is focus on converting one-way door to two-way door decision. That'll actually get you a lot of value. If you have one-way door, see how you can make it a two-way door. Or if you have, especially when I see multiple design choices, try to make your design independent of the choices. So let me give an example. So let's say you're deciding between which workflow technology to use, step functions or simple workflow service. What you want to do is you want to decouple your design from that decision. You want to take a step back and say, yeah, I need a workflow. That's what I need. And with these properties, I need a workflow system with these properties. I don't need a design. I don't have to couple my design to a technology. So see if you can start doing that. It's not always possible, but make an attempt to do that. Okay, so with that, I've completed 4 things. The 5th one is design span. This is extremely important. I was actually figuring out the order because multiple times I changed the order up. So should this be above 4 or below 4? But let's go into this to see what it is, right? Design span, like as I spoke about the themes, design is for software evolution. So the quote is, design is for the future, but you build your software for today. Now the question is again, how long is the future, right? Is it and that future is your design span. Now, for design span, what do you look for? The first thing you look for in a design span is, do you have an incremental plan? So in your design document, you've laid out a design which is actually talking about all the good things. Is there an incremental plan? And the incremental plan is possible if you have good decomposition. It was, and goes back to abstractions and decomposition. What are the decomposition? What are the different components? And what are we building in each phase? It's impossible to build everything at once, right? You want to have an incremental plan to actually build. Like complexity, you want to build that upon incrementally. But so as you look at the incremental plan, look at the decomposition and look at those decompositions and figure out what you're trading off. For example, not building a configuration system, storing configuration separately could be a trade-off, right? And that is something that you be aware of on each phase, right? So with that, right? uh, you know, keep this in mind. And with that, let me move on to the next point, which is I want to cover, which is flexibility, right? Now, before I cover flexibility, I want to talk a little bit about complexity. And one of the important aspects of software design is complexity. Design should be as simple as possible and as complex as necessary. Problems should be complex, but the solution should be simple. Now, how do you know if something is complex or not? Now, when I ask a lot of people this question, many senior engineers actually tell me, "Yeah, I know when I see it." However, complexity makes the software hard to understand and reason about. And it's true, right? If you can't understand something or reason about something, that is complex. And there are two aspects that you want to look out for in complexity, for managing complexity. One is modularity, problem decomposition. You're breaking the problem down, going back to the themes, you're breaking the problem down to manage complexity. The other way you add complexity is by flexibility. Too much flexibility, especially with incorrect abstraction, leads to tremendous complexity. And let's see how. Flexibility definitely increases complexity. And one way we do flexibility in software is configurations. Now, configurations are used to make software flexible. They are basically parameter and switches that allow you to change the behavior of the code. So you actually take it out of code and put it separately so that you can tweak it to change the behavior. Now, with configurations, I've seen a lot of challenges and a lot of complexity getting added. So let me dive into that, but let me explain that with again, a real world analogy. Now, one of the key aspects that I want everyone to remember when they work with configuration is standardization versus customization, the trade-off between these two. So let me explain this trade-off with an example. Standardization improves efficiency. Like let me give an example of a Swiss Army knife, which is a great all-in-one tool. It's one tool, and you can use this to do a lot of things. You can use this to, in your kitchen. You can use this to repair your plumbing. You can use this to, fix your electrical, almost everything. This is an example of a standardization. It's a standardized tool, and it is efficiency. A standardization improves efficiency. And why is it efficient? This is cost efficient because there's just one tool. It is size efficient, and so on and so forth. While standardization improves efficiency, it reduces effectiveness, especially effectiveness in terms of customer experience, right? It's not a great customer experience. It's not very effective in terms of customer experience. I'm not going to, I can cook with this, but it's not really it's not a pleasant experience cooking with this. This is possible, right? And a good chef will not use this. Instead, a good chef would prefer customization and something like this, right? A set of kitchen tools, where in this case, you have multiple tools where, one for each, just a set of kitchen tool and one for each item, right? Now, in this case, if you see, this is a great customer experience. It's super effective for the customer. Great experience. But it's not efficient in terms of size or cost and so on and so forth. So this is what I wanted to highlight, right? The standardization and customization. Customization makes you more effective, whereas standardization makes you more efficient. Now, it's not an all-in-one. You can't get both. You can't say, I'm customized, I also want to be efficient, right? You want to understand, you want to kind of come somewhere in the middle, right? And you have to understand the trade-off to arrive at the right mental model. So let me give you an example of standardization and customization with respect to configuration. You are an e-commerce website again, and when a customer does a KYC, going back to the KYC example, you want to give an option of making a payment, right? And now you have three options. Let's see three options. One is, let's say in US you want to support credit card, but in India you want to support credit card and bank. Typically, you would not want to write this as a if condition and code, so you kind of take it out and put it as a configuration in any favorite language you like, and you sort of define it something like this, right? So you have two entries. Now, this is an example of customization because every time I want to add a new country, I have to add a record here. So it is effective because now I'm giving Indian customers two options, whereas but it's not very efficient. I have to keep adding things. Now I can make it a little better in the sense that what I can do is I can say, okay, everywhere the default is credit card, but in India use credit card and bank account. Now, what I've done here is I've moved in the spectrum from customization to a little standardization. So I can launch new things and they'll get credit card. But when I want to customize, I cannot do this. Or I go to option 3, where it's standardization. So let me give you an example. No configuration. Worldwide use only credit card. So it's very efficient. I don't have to do anything to this software when I launch a new country. or expand, support new countries. What happens is that but it's not a great customer experience. So you have traded off effectiveness for efficiency. So this is an example of standardization to customization spectrum. You're not going to get both. You want to think about this, question yourself, and think deeply about this. So with that, the key takeaways on flexibility are there's a trade-off between standardization and customization. So keep that in mind, especially when working with configurations, because not having this in mind results in too much flexibility and complexity. And the important thing that you want to ask yourself is often it becomes hard to differentiate what is code, what is configuration, what is data. It's very hard at times, right? And sometimes it's clear. Like, for example, if you are setting up a configuration for a web timeout, right? A web timeout setting up, that is configuration, right? Timeout or an endpoint for a web. You wouldn't put hard code an endpoint on the code. It's a configuration. But it becomes tricky, right? If you have, let's say, tax rules, tax rules for a country and complex tax rules, you don't have them in code. You probably have taken them out, but are they really configuration or are they code, right? Even though you've taken them out. And the other thing to look, similarly, if you have complex accounting rules, are they config or data? So while we think code, config, and data is something that's obvious, it is not very obvious. So keep this in mind from that perspective, because you want to clearly define what they are. Because understanding the difference plays a key role in what technology you'll use or what solution you'll use. You'll store code in a Git farm, but you'll not store data in a Git farm, right? Similarly, you'll not store code in a data store. So similarly, and this difference helps you, deal with complexity and manage flexibility in a very efficient way. So with that, 6 things I covered, from mental model to flexibility. And with that, let's go to the last aspect, which I call elements of reuse. In elements of reuse, I'm going to particularly cover patterns. Now, patterns are generic solutions that worked previously for recurring problems. Now, they are successful engineering stories, and they give you a common vocabulary to talk about. So what you want to see, when you look at a design, when you review a design or when you're doing the design, see if there are common patterns that you can use. And, can you take your design and map it to a pattern, right? Can you map this to a pattern, or is there some inherent pattern there? Because patterns are successful stories. Then once you find a pattern out, you can actually discuss and debate and get other people to talk about. Like someone else can come and tell, I've used this pattern and these were the benefits and these were the pitfalls and these were the challenges. So figure out, right? So highlighting patterns. When I talk about elements of reuse, look for patterns throughout in your design, all the way from architecture to code. Look for patterns, see what they are. So that kind of gives you some more highlights. And architecturally, especially with high-level design and service design, this is a typical pattern that you follow when you design a microservice. It's a 4-layer service design. And what happens here, there are 4 layers in a service. The clients talk to a layer 1, and communication with the dependencies happen through layer 4. And layer 2 and layer 3 are used to implement your business logic. Now, why do you do this? Is that the layer 1, what it does, it exposes an external model that your clients can use, and that external model is translated to an internal model at layer 1, at the boundary of layer 1. So now layer 2 and layer 3 operate with the internal model. Similarly, layer 4 does the reverse for a dependency. So the external model exposed by the dependency is converted into an internal model. So 2 layers you have for managing your business logic work with internal models. So this gives you a beautiful decoupling. So if your external model changes, your internal, just one layer gets impacted. And similarly, if your internal model changes, it doesn't directly impact the external model. So it gives you decomposition. Usually you can have more layers in between, but generally 2 layers is I've found useful in most cases. But if you want, you can add more layers. But see why you can't put 2 layers in before you add more layers. But this is one example of a pattern to look out for in high-level/low-level design. So with that, I'm going to thank everyone for attending this talk, and at this point take questions. But broadly, 1 to 7, right? Look for a mental model in your design. Look for abstractions, and especially are they over, under, or right? Keep all of those in mind. Definitely define your tenets. Look for reversible and irreversible decisions, one-way, two-way doors. Look for design plan. What is the incremental plan? Look for flexibility, right? And especially the trade-off between standardization and customization, looks for elements of the use in pattern. With that, I thank everyone for attending, and I'll start taking some questions. Thank you.
Awesome. Thank you so much, Banks. Love the way you described software design in a clear and simple way. I'm sure it was very useful for everyone in the industry. We already have a lot of questions lined up for you. I'm just going to go right into it. All right, so we'll go with the one most upvoted. So the first one on the list is this is a question from Noor, and she's asked, the abstraction you mentioned is great to show someone at a high level what the system does. But there is a need for detailed component level design for engineers to understand the inner working of a system. Further, the design choices are also influenced by the detailed design and technology limitations. Where and when does the discussion on detailed design or low level design come into play?
Noor, great question. Thanks for asking this, right? So, let me answer that going back with the analogy. So if you see the example that I give, see, problem decomposition is you have a big problem, and so you want to break it in, right? Now, at the first step itself, if you break it into lower level components, think about it. If you have to design a KYC system and you're directly talking about the classes, you'll have like hundreds of classes. So it's very hard to directly jump into that level, right? To directly jump into the number of classes. So what you want to do is you want to follow a layered approach to decomposition. The first one talks about 7 plus 2 components, right? You come up with an architecture that has 7 plus 2 components, all at the same, operating at the same level of abstraction. Then you take each component out and again drill down. That becomes your high level design. So again, come with 7 plus or minus 2, again drill down. And at a certain point, you will actually come up with low level design where you will talk, talk about the 4 layers. Maybe it's a microservice, and you'll use the design that I spoke about. And then what you will do is you will take that, and from that you'll start writing code. Now, so that's a layered approach you do. But remember, directly writing code is, I give you the example. Directly writing assembly is it's not maintainable. It doesn't allow evolution. It doesn't allow teamwork. So you'll have to do it in this way to kind of get to the actual design. And again, going back, right? Design is all the way from architecture to code. So I want to talk an analogy here in terms of real world analogy. So this can be anything, right? It could be making a phone or making a or a building, right? So let's take building as an example. How do you design a building? You come up with the overall design. Architect creates a design, and then what you do is there's a construction team that takes the design and builds the creates a building. Now, what is the equivalent in software? So I would argue that all the way from architecture to code is that design, is that architect's job. Where's the construction team? The construction team I showed you, it's the compiler. The compiler takes the code and makes it working, the actual artifact, the building, in this case, the assembly code, right? So keep that in mind. You're doing this so that you can work with the team and you can actually decompose the problem. So the roundabout answer, but I hope that I've been able to answer that question. So Nabil, over to you.
Thank you. Yeah, that makes a lot of sense. Next question is from Tara, and the question is, sometimes we've given multiple design approaches to solve one problem, and each of them have their own pros and cons. What's the main criteria to choose the best one?
Makes sense. Tara, always difficult questions from Tara, like as always. So, as I told you, the right thing to do, one of the things I didn't talk about here is the paradox of choice. If you have too many choices, right, what happens is you don't end up making a decision, or you take a lot of time and end up making a suboptimal decision. So that always happens, especially with me. So what I would like the team to do is, when you have a lot of choices, like see if you can make things. First thing is, what can be agnostic of the choice? Not everything can be. At certain point, you have to use a technology. You have to code either in Java or in some other language. You have to either use AWS or something. So the question is, what you want to do is you want to keep all the way from architecture to high-level design as independent as possible, and start coupling design as late as possible, right? Even in your architecture document, right? So because then you're talking about the important aspects. Technology keeps evolving. Today you have a certain version. Tomorrow, especially front-end technologies. I've seen like so many changes over my career, right? In terms of, so you want to decouple your design as much as possible and explain the main concept so that you can aid evolution. So tomorrow, if that technology gets deprecated, people know how to apply. make the design choices, keep them at the, appendix, right, of your document. If you're putting it, put all the choices and analysis at the appendix. But in your design, talk about what you need and what are you using. So definitely you have to use choices, but defer that as much as possible. That's the only thing I would say, and that'll help you come up with more design. Otherwise, going back to the example of KYC where I used API Gateway, DynamoDB, and SNS, right? That example, if you think about it, that design fits any use case, not just the KYC use case, right? So there's no design there when I talk about technology choices. That's what happens, right? So when I spoke about the right abstraction, I was talking about the problem domain and the abstractions. So that's what you want to do in such cases. So that's a very, very good question. Thanks for asking that question, Nabil.
Yeah, I think you put it the right way. We had a few discussions, you and I, on this, that leaving it right to the end, that makes a lot of sense and simplifies your thought process. The next question is a bit long and a bit away from design and more into code, but I think it's a very good question and we should go into it. So the question is about, Muhammad has asked this question. And he says, we're developing a prototype, we're developing a proof of concept. We want to test out a few things. We want to see the user experience and so on. In that case, if the solution is not optimum and the customer don't like it, they might get rid of it. And he's asking if adding unit tests in that kind of solution, what's your take on that?
Great question. Okay, so before I answer the question, I'm going to give long question, so I'm going to give a long answer, right? But before I answer that directly, I'm going to take a step back. Writing. So a lot of times people tell me writing tests takes far more time, right, than writing main code. But the thing is, there are two aspects to remember. If you write tests along with your main code, and as you become good at doing that, right? Initially, it takes time because you've never done it. You will find it slow. But once you get to doing that, right, it's not that slow. The difference is marginal. Yes, right. Test means extra line of code, but over time you become good at it. But if you never do it, you'll never become good at it. So keep that. A lot of practice comes to raise the bar on that. The first thing is that. And second is tests pay off. Very, very soon, right? Because once you have tests and you want to refactor something, it becomes easy because you have tests. You can take the entire thing and take it out, right? Look at the layered design I talked about, right? If you have tests, you can take the entire thing and put a new thing in because tests work. It allows refactoring. And so it really pays off when team members come, when you're not there, and so on and so forth, right? So that's on broad thinking on tests. Now, when you're doing prototyping, coming to that as the real essence of the question, it's optional. It depends on where it is. So definitely you have to use your judgment there. If it is, it's truly you're learning some new technologies. Like I was prototyping AWS has launched a new service framework, Smithy. And I was prototyping that. So I was playing with that a few days back. And I did not write tests because I was just playing. I know it'll never hit the production, but the minute it hits the production and there are other people who are going to work for it, you have to empathize because you are not here just developing software for yourself. You're here for the team. So then start writing tests. But that's a judgment call. But the reason I say it's a judgment call is many a times a prototype actually hits the production. What do you do then? Right, so you'll have to start foreseeing those and do that. But what I would generally, recommend, going back to the first two things, is take a step back. You want to be solid engineers. You want to become better. The only way you can become better is by actually trying and writing more tests. You cannot become better by writing crappy code, right? And over a period of time, as you write, especially I get a kick when I write high quality code fast, right? So that takes a lot of practice, and that's what all of us have to achieve, right? Doing the other one is like way easy. Let's not do that.
Yeah, that makes sense. Cool. We run out of time, but I'm going to take another question. I think is a lot of upward on that and makes a lot of sense. Again, a bit long question, but I'll try to paraphrase it. So the question is from Omar, and he's asked, when you're reading code from someone else, right? You joined a team and you're looking at the code. And sometimes you have to start from one piece of code and then you have to keep going up and up and up till you understand the whole flow. Now imagine you are that person who you don't want to be that person, right? What is your advice to add? What kind of abstraction we can add, both at a design and a code level, that will simplify it for the person who's next reading the code?
Yeah, very, very good question, Omar. And just to take a step back. Ideally, like if you have used the 4-layer service design for your problem, assuming it fits, and you know what the layerings are, right? that's where you start. Like if I have a package, I know what the layers, I know this is the client layer, I know this is the dependency, I know these are where the business logic is sitting in, right? So that's one, gives me a broad thinking to reason about. And then you can go and look at appropriate classes. And inside the classes also, you can have a spaghetti. So fundamentally, the answer is don't have a spaghetti. Make things easy to reason about. And the only way to make things easy to reason, you have to give a big picture. Otherwise, you cannot reason about things. Like if you want to, create a map of, let's say, Middle East, just looking at one, city is not going to help. You have to take a step back, zoom in. Yeah, I know where things are now. Then kind of zoom into specific places, right? That's exactly what you do with architecture, high-level design, and code. And that's what you should take a step doing. So broadly, that's the question. Ensure you have these in place so that understandability be easy. Definitely use some sort of organization and package structure for your code. And in this case, if you're using the 4-layer design, like put that and standardize that and put a README in. So usually that's one aspect, right, at a broader level. When it comes to class documentation, especially if you are writing a public documentation, this is my thought, and again, this is a very debatable topic, but if you're writing public documentation, I would like you to take a step back and think about writing good documentation for the interfaces. But if you're writing an internal class, don't write a lot of unnecessary documentation. Code should explain itself and make the code simple, right? That should be your priority. Usually I would always write a top level documentation for my class. I usually start my code that way, write a top level down, what it does. And usually I write that I have this constraint, I write that in 25 words without using if, and, or but. If I can do that, like then I know it's doing one thing easy to reason about. So that's the only documentation I write for an internal class without using these 4 letters. And then I kind of take the necessary, document. Don't write too much, that will be clutter. But these are some techniques you can apply to do that, and it's just there's just one answer to it. There's a lot of things you need to do, right? And it starts with you, and the excitement is raising the bar doing it. So with that, Nabil, thank you so much. We are right on time.